Okay, so we are live. Yeah, we should be live now. Good. Guys, wait a second. Like, if you're, I'm gonna wait a bit. I just started like a bit earlier because I want to make sure the setup is working well and better than last time. I hope that I'm gonna get the voice coming from Discord smoother because last time I was using a microphone. I was using basically the microphone from the laptop and. Because for some reason Discord seemed to to not catch my voice through the microphone, and I didn't want the other guys to hear me. I wanted the other guys to hear me well through the voice channel in Discord. So bear with me a second. I'm gonna try to see how this looks like on the other side on my phone. See if that works at all. It's loading. Hi there, guys. Let me know if you can hear me and see the. See if that works at all. Yeah, seems it's working. I hope there's not a lot of background noise. And let's see. I don't know if we're gonna actually have a discussion. It's just rather gonna be me solo talking about stuff, because everyone else that's guys, let me know if you can. Sorry, I had the stream on. Okay, cool. Let me just. That seems to work. Um, so I don't know if it's going to be just me by myself or someone else going to join from the Discord server, because the most of the people that are on the Discord server and the actual quantum paper club, they are also in the Qiskit summer school, and I think that the lecture from today just finished, so their brains are probably fried right now, and so I don't know. We'll see. But I got some questions. I got some questions from some of the people in the server, so we can go through these and just kind of roughly talk a little bit about at least my experience reading the paper. We'll wait a little bit more, a couple more minutes, see if anyone's joining. And the Discord so far, I'm still alone, but that was expected. So let's see. Although other than that, I mean, I don't know. I also I see there is always a delay with the messages, and I'm really noob with streaming, so I don't know if this is something that I can configure or not, because the comments seem to come in sometimes late. So if you say something and I don't react to this, or nobody else reacts to these, be patient. I'm gonna get better with time. Actually, I'm thinking to actually switch to live streaming a bit more, to actually do more live streaming in the near future, because I kind of like the format as well. I like the no. It kind of feels a bit more like having a conversation. It's just that I don't have a perfect setup, and it's weird because I don't have a I don't have such a bad machine, to be honest. It's like 6 cores, but it seems like the streaming. I mean, now I got it right. So I'm using OBS, and it seems that it's working well. So we'll see. Got some people already here watching. That's nice. Hi everyone who's joining now. We are going to be talking about the quantum machine learning paper. For those who don't know which is this paper, it was shared in the Discord server. By the way, if there's anyone right now watching that is not in the Discord server and wants to join, let me just drop an invite in the chat, because I think if you guys are interested in joining, it's always nice to have more people on board. Let's see, how can I invite people? So I'm gonna create a link that is going to be valid for like 1 hour or something, kind of the duration of the stream. And I'm going to share it here in the chat. And if you guys want to join, you're welcome to join. I hope you can see the invite. Yeah, cool. Perfect. Good. Otherwise, people might be joining in late because we were having a chat this week, and they're like, everyone's kind of in between the summer school lecture, the Qiskit summer school lecture, and the actual lab. So a lot of the people are probably, as I said, like they have like a a fried brain right now. But if nobody shows up like in about like a minute or two, then I'm going to start at least with the with my comments from the paper. So we're reading the paper that is reading. I read the paper that was suggested in the channel. It's called Quantum Machine Learning. and it's by Jacob Biamonte, Peter Vitek, Nicola Pancotti, Patrick Rebentrost, Nathan Weber, and Seth Lloyd. So wait a second. There's one of these people is from Spain. I'm from Spain. Okay, but this paper is from 2018, and let me see. Someone's like, okay, some people are joining. If you're joining the Discord server and want to join the conversation, go ahead. Like, you can just join the voice channel, Quantum Paper Club, on the bottom, and I'm happy to, I mean, you'll be live. Be aware of this because I'm I'm streaming this. So if you don't mind being live, feel free to join the actual voice channel in the bottom, and we can have a chat about the paper right now. So I see some people joining the Say Hello channel. Eigen Charlie. Nice. Cool. But yeah, I mean, let's just. I think I'll just get started. Jacob is teacher in code tech. I mean, maybe first a disclaimer, right? Like, I'm not an expert, and if you've been following me, you know these. You know that all the stuff that I do in this channel is literally I upload my raw learning experience, and so the only reason I'm doing this is because I hope that it will be somewhat somehow useful for the future, for to kind of see how someone is really learning. And you really see everything from like there's no preparation to most of the videos, right? So these weekly quantum discords is maybe the only discussions where I actually read something in the background and then I'll discuss it in here. Can I share? Yeah, sure. Feel free to share links, and if you guys join the Discord, like, explore, enjoy, have fun. It's a server from learners to learners, and no matter what level of expertise you have, if you're like a total noob or like a pro, then just feel free to share stuff. We're really building it up, so keep that in mind as we keep evolving the server. We're changing and moving a lot of stuff. So and I'm gonna definitely, and I think we should definitely add a QML specific discussion channel or something like that. But anyway, I mean, I'll just go ahead. If someone wants to join the discussion, happy to do so. Just click on the invitation link that you see in the chat and join the Quantum Paper Club voice channel that's at the bottom of the channels list. Not the text one. There's a text one where we organize stuff, and there's a voice one at the bottom. So feel free to do so. Good. I'm really just going to go straight and kind of at least give you my rundown of, how I found the paper. The paper, I mean, again, this paper is from 2018, and when I tweeted about these, Guillaume from like Google AI, sorry, not Google AI, but like the, is it the X team, I think, right? So he mentioned that this is, in terms of QML timeline, this is an old, it's already outdated, right? In terms of this paper was written before the whole variational boom in terms of all the VQE and all this kind of algorithms. And so, but having that in mind, I thought it would be an interesting paper to kind of go through and skim through and see whether there's anything that like at least gives you a rough idea of the status of the field. I mean, maybe I came in wrong. Like, I started reading the paper maybe with the wrong expectations. I thought it would, the paper would go a bit deeper into some of the subjects, but it doesn't. And so I think from what I expect from the Quantum Paper Club is maybe something a bit more concrete, but we'll discuss this with the guys. Because these papers, like after reading these papers, I really don't feel like I'm learning anything, but rather, kind of getting a bird's eye view on what is being currently researched in the field. And I think it's kind of nice from one side, but it really felt like it felt like something impossible to do within a week, because to really take something useful from that, I would have to dig into the references, right, and actually really dive into each of those different aspects of what's presented in the paper. So the paper basically kind of talks about the importance of quantum computing from the context, not only from the context of machine learning, but like, it kind of gives a really well-rounded view across where is quantum having a good impact, and where is also machine learning improving and helping on the quantum side, right? So, and I mean, let me, because I'm going through this before I jump to the questions that I have in the Discord. So the paper really focuses on the sort of the more linear algebra based or types of improvements, right? CJ is saying the paper was really a general look, kind of like a Wikipedia article, good for bouncing off. Yeah, exactly. But that's the point. Like, I expected that within this week, I would be able to take something more concrete out of these. And then, reading the paper, I didn't have much time. And so reading the paper, I felt like it was a bit overwhelming because I didn't, for me to take something important, I would have had to actually really dive into some of the references, which I didn't do. And it's kind of bad, but I guess that's the reason for these papers to kind of exist, right? I'm getting notifications. Swaggy Niba. So Abby is joining the voice channel. Hey man.
Hey Daniel, sorry I was late.
Yeah, no problem, man. How was the school? How was the Kiskit school today?
It was nice actually. Actually, due to some technical difficulties, the you can say lecture could not be completed on time. So there was things that could have been said or that could have been added to the lecture due to the shortage of time being 3 hours. Actually, HVC is a big topic. It was not correct to actually just allocate 3 hours to it. It requires more than 3 hours, of course. So yeah, it was fine. It was a nice lecture. The petition code was well explained. Unfortunately, he couldn't properly explain the surface code area, but yeah, it was a nice lecture. Nice 3 hours.
Okay, cool. But it was. You're saying it was basically too much to get done in like 3 hours. I would love to next week. Like if you guys are done next week, I'd love to do the weekly quantum Discord. I think we talked about it already, and kind of you guys giving your Roth experience, like a summary of how did the school go.
It will be cool.
Yeah, sure. Yeah, sure.
For those who are like in the chat, like Voikutu and Swaggy, like whenever you're not talking, try to mute the microphone so we avoid like the problem that we had last week with the noise. I think it's going to be a better for the live stream as well later on. I don't know. I was kind of giving. I don't know if you were listening to me, but I was giving my opinion on the paper. And again, I think that it's a bit of a too generic kind of an overview paper. And I really would like, next time that we kind of choose something a bit more concrete that we can play and get our hands dirty with, because that's kind of what I felt after these. But it did help me. Because I saw again the QRAM concept mentioned in the paper, and I took some time to actually dig into these, and definitely not enough, but I at least I got to dive into this a bit more. I mean, what was your take from the paper?
Actually, I'm not quite into QML right now, but what I can say is that it's a 2-year-old paper. So things have got better since this paper was published. And basically, it was a general paper. It was a very general paper. Although I have no idea about machine learning, but still I was able to grasp almost the basic concept out of this paper. And the things which I wanted to ask that the paper highlighted some problems which we are facing with QML, like inputting. How will we input classical data into quantum algorithms? How do we, you can say, measure output, and how do we extract the relevant information out of outputs? So if anyone from the chat is well versed in this topic, I would like to learn more on this because I do not have time to dig into it myself. So I would love to hear about it.
Yeah, that was my point. That it was difficult to actually be able to dive into some of the linked resources, because I do believe there's some relevant papers linked into there. But it's, I mean, for me, what the paper says is the input problem, the output problem, and the what was the other problem?
Benchmarking.
Oh yeah, the benchmarking. But like the benchmarking is less currently for me less interesting, because it's a bit more like we haven't even solved it with classical machine learning, as in it's really complicated still to make any statements in terms of whether a machine learning technique is like, scalable. It requires a lot of kind of empirical data, right? Like trying a lot and see how it scales. The input and the output, basically, what the paper says is the input problem is that it's for some algorithms to be able to kind of have an impact. You really have a bottleneck in terms of how do you get the data loaded or ready for a quantum computer. For example, when they talk about like the principal component analysis, right, where they say it's great because a quantum computer naturally can represent the covariance metrics by virtue of having the density matrix is the covariance matrix. That's what the paper says, and so the problem is that kind of getting all the data in there, it's a bit more complicated. I don't know if that's exactly the case where this is really a costly example, the PCA one, and but that's where a lot of people kind of put a lot of hope in the QRAM, in the quantum RAM being a solution for these. And the output problem is, well, it's a sampling problem, right? It's like what other algorithms also have, even if it's not QML related, is that once you have a quantum system, once you've run your algorithm, if you haven't done this in a way that you've interfered stuff so that it's easy to get the answer out, then you're going to have to sample the thing. And then sampling means running multiple times. And yet that's going to create overhead, right? So I guess that's the point.
Yes, I believe if we will have a quantum computer big enough, some of the input and output problem will be solved because we can do more in quantum.
But I mean,
for example, if we apply PCA and after this we make the next step of the algorithm still in quantum, we don't need to do other things. It will be more efficient.
Yeah, that's the point. I mean, that's exactly. And I remember reading these in the O'Reilly book as well, saying that that some of these algorithms will definitely work better if you can kind of plug already whatever you want to do. You can plug it in within the quantum computer. So after whatever you're doing with the QPU, you do the next stuff. So you don't have to take the data out of the quantum computer. That's the problem. Like when you have to take it out. I think here, regardless of the size of the computer, of the number of qubits and whatnot, and the fidelity, it's something you want to avoid. If you want to get the data out, that's kind of the problem. But because the QRAM does try to solve, I think, the input problem, and I did dig into this before in the last weekly Discord. I was confused because I was not sure what it meant, and now I can confirm that. At least it's really about accessing memory or addresses in superposition. I think kind of that's the idea, right? That you have the data prepared and indexed in a way that you can then, with this QRAM, just basically pull it up and get your superposition ready, so you don't have to prepare the state. I think the problem is this state preparation. That's what's slow, right? But the assumption is the QRAM, if it's implemented in a way that it's not slow, then the preparation of the data is classical rather than quantum. So then it's it's kind of not counted in terms of the costs. I don't know.
Yeah, well, it comes down to actually implementing QRAM because we are talking about storing superposition rather than actual values.
No. Are you sure? Are you sure they're talking about storing superpositions? I think it's more about you store data, right? And you can access it in superposition. So you're not storing superpositions, you're storing data, right? Like in like it would be like a classical RAM, right? Like in address 1, there's this bit of data. In address 2, there's this other piece of information. What you can do with QRAM is you can access the address 1 plus 2, right? Like you can access the both elements and kind of get them loaded into superposition directly on your side. So that's you're saving up on the preparation. But again, I'm really noob in this, so I've just scratched the surface, and I'm definitely going to do a series on that at some point.
Actually, you might be right because I might be getting confused because actually I was also reading a book, Quantum Computing for Computer Scientists. I think you must have heard about it. So actually, it has a chapter on this QRAM, or you can say implementing quantum computers. So what it does is it took an approach. It basically says that an hybrid approach is the most you can say formidable or closest thing we can get to a quantum QRAM actually. So what they said is that you actually need to store superposition in order to basically utilize the full the capacity of a quantum computer rather than actually addressing them in a superposition. Because addressing in superposition it doesn't make sense to me, to be honest, because
I would say
doesn't make sense to me.
I would say
Can you elaborate? Can you elaborate? Because it didn't make sense to me. It was not intuitive enough. So
I
I'd
mean
like.
I would say it's the opposite. I would say storing a superposition is what makes no sense. And again, I think we're I mean we're both non-experts, but like I think because the point of a quantum computer is that you can have like the computer has the superposition information, and that's what's hard, that's what's difficult to simulate classically, because if you have 100 qubits, then you can have a 2 to the power of 100 superposition, right? And to store this is impossible because it's more, it's bigger than the number of atoms in the universe, right? Like or I don't know if that was the exact number, but like that's the point. Storing, I think storing is what doesn't make sense unless you're somehow storing the qubits separately and then you're just recovering that by loading the data into each qubit. Maybe that would be a way, but like storing each, but I think that doesn't make sense either, right? Because if you store the qubit information separately, that's impossible because essentially you can't store entanglement or information that's at the system level, right? So I think that's what I.
Yeah,
Right, this is the reason, because I'm so confused, because I don't understand how you can store information
No, you
and
can't. That's
reuse it.
Yeah, that's the
And
point. You can't store it. Like that's the point is that you can't store it. So
yeah,
what the QRAM is doing is helping you load classical data into the quantum computer. So the QRAM holds a representation of your data, and then you can address it in superposition. So what you can do is, with a one call to the QRAM, you can load up all your data in the amplitudes of your superposition. That's at least the way I understand it. I guess if anyone in the that's in the live stream right now like has any good resources or anything, and like we're more than happy to to learn more about these. I don't know what else other than these, like other the input and the output. I have some questions here from Voiku too. I hope I'm pronouncing your name correctly because you're here also. Okay,
Voiku,
Voiku. Okay,
just Voiku.
just Voiku. Okay, cool. Because you ask, like, do you think QC could open the door to new machine learning algorithms different from what we know so far? After all, it's a new way of thinking. To adapt the classical algorithms is useful, but still. Man, like, I totally agree. I think I really, I really agree with the sentiment behind this question. Because I'm in quantum computing, I am less worried about speed ups, and I know that most of the people are, in the industry or in the field because of the speed ups. But I'm in this mess more for the new kind of stuff, right? Like the stuff um, that's kind of more quantum, uniquely quantum, so to say. And I really hope that there's going to be some breakthroughs in machine learning that are not like the current deep learning model, right? Like where you've got like the layers and the neurons and all that stuff. I don't know. What's your perspective in this? What do you think?
I'm sure it's something different, because if we just speed up things, it's not interesting. Like we need to spend more time in quantum work to understand it better and create complete new algorithms that are different in everything. Like
Yeah.
thinking in quantum, not just speed up
Yeah, not just speed ups
what we
over
already know.
classical stuff. I mean, this is an interesting question because, and I think this is where all this variational stuff is kind of a good step towards these. But I'm not really sure. I mean, of course, if we knew what to expect, then it would not be innovation, or it would not be new by definition.
So,
Um,
sure.
but maybe there's something kind of related to the fact that there's all this information in there, and I to some extent I smell that if there's going to be some interesting developments in this direction, it's probably going to be something that's using entanglement, something that's using this kind of resources which are really truly and uniquely quantum, right? Like, because the fact that with the quantum computer you can somehow speed up some of the linear algebra stuff is just I don't know. It doesn't appeal to me so much, right? It just happens to be this way. It just happens to be the way that quantum that the quantum stuff works, right? It can be modeled with linear algebra, and so you can speed up things to some extent. But it doesn't feel like that's purely because the linear algebra model of quantum computing, really I feel it kind of, it's a really shortcut, like a tool to work with this confidently and comfortably, but it doesn't really let you explore the true quantumness of it. And I know that I might be sounding too fluffy and probably I'm talking too much, but I think there's got to be something else there. Like I don't know, even trying to think about like kind of to me it's a bit more like what happens, you've got like all these concepts, right? Like a superposition, and then you've got the entanglement. And entanglement, you also have sort of different notions of how much something is entangled. You also have different types of correlations, actually, right? Like discord, discord is another type of is another a way to measure the type of relation or correlation within a quantum system, as far as I understand. There's more than just entanglement. There's also quantum correlations in general, and then there's classical correlations as well. So there's a lot of stuff to explore there. And I don't know, maybe we should pick a paper on entanglement as well next time.
This is exact my point of view.
That's cool, man.
First of all, I stand corrected. You were actually right. You cannot store information in superposition, but you can get information from a superposition. So yeah, you're completely opposite of what I said. So I stand corrected.
Okay, cool. I mean, yeah.
Yeah, and I agree what you're talking about, because I was listening while I was searching and making sure that what I did was wrong. So okay, so I feel you're right saying that. So currently, we are the state at which we actually are implementing you can say quantum machine learning for optimizing the current machine learning models. So we are not actually utilizing the full potential of what quantum mechanics can give us, like as you said, entanglement and all. But what I feel is that entanglement can give us a better, you can say, convolution between nodes, and you can say a better efficiency. But it all boils down because currently we're limited to thinking of quantum as an optimization, you can say optimization method. So for now, I think we are thinking is stuck until something new comes up. Of course, to be actually you can say describing this quantum machine learning to be an optimization step and in improving this classical machine learning, because as some have suggested that we might be entering, and you can say an winter age of artificial intelligence. So until something new comes up, which according to me, quantum machine learning could be the next thing which actually gives a new life to artificial intelligence, because if nothing happens in QML.
Yeah, I mean, you said something really interesting. So you said the entanglement can give us more. How do you phrase it? Like, I mean, it's not that it's not used; it's used, right? In variational quantum machine learning, or in variational approaches, like you have an ansatz and you build an ansatz that you can build it with entangled qubits, and so entanglement there gives you a I think it just makes the space that you're going to explore bigger, right? Than what you can with a classical computer.
Like a hyperplane. I think it improves the hyperplane, sort of that division of data. It gives you a better, you can say, difference between the two data which you're comparing.
Exactly, but my point is, I think we're not using. Maybe we're, and this is probably totally naive. If there's someone expert watching and listening right now, they'll probably make fun of me. But I feel maybe we're not using entanglement in the right way. Like if you think about the many worlds interpretations of quantum computing, right? Like where you have, to my current understanding, the idea is we're constantly being entangled with stuff, right? And so we're constantly being forked into different parts of the, this universal like how's it called? I forgot the name. Like whatever the function is, right? The wave function, exactly. And so this kind of entanglement that happens, right? Like I feel the dynamics, like the evolution of entanglement through time is something that we're not maybe exploiting enough, and maybe the next level of machine learning is not anymore a an approximation type of model where you've got these neurons and you build the different layers, but it's something totally different. That's my point. Maybe it's something totally different that you set up a system and then you let the system run, right? Like you let the system entangle with stuff. Then with the environment somehow. There was something really interesting in the paper. Like the paper talked about quantum simulators, but I think what they really meant is, or what they're meaning there is a quantum simulator being an actual quantum computer, right? A computer that simulates a quantum system. And they were talking about a quantum the possibility to use a trusted quantum simulator to understand more stuff about an actual quantum system, somehow to connect a quantum computer to a quantum system, and then you do something in the quantum computer that, like, I don't know what it would be, but something that then helps you probe the unknown properties of this quantum system somewhat. Maybe you entangle it somehow, I don't know how this interfacing would look like. But maybe this is the way. Like maybe this is maybe this is kind of the path to better machine learning, where we get a computer and we literally entangle it maybe with another quantum computer, or we entangle it with something else. We connect it. I don't know. Maybe entangling is the wrong word, but like you connect it to something else, and you kind of let the stuff evolve and see what happens. I don't know. It's really I'm really kind of dreaming probably here, but it's something maybe different than just the variational kind of stuff. The variational stuff, it's definitely, I think, gonna lead to some interesting improvements, but I don't think it's kind of the way. Well, I sense it's maybe not the final solution, right? Like someone said, I was watching a stream from George Hotz, where he's like, someone asked like, is GTP, or is it GTP3 like the singularity, and like is it like really the actual beginning of an AGI? And he's like, maybe if you scale it like 100x, it can be dangerous enough. But I feel like that's not it, right? Like I don't know, that's not really the path, I kind of feel. But maybe it's just me, I don't know. Have any of you used D-Wave, by the way? Because I was, Voico, one of your questions as well.
Yes, I heard a lot about D-Wave, but I don't know a person who use it.
Because it somehow
Did you use it?
No, I mean, I think actually my first video in the channel, it was a video trying to run a demo on the D-Wave system, and it didn't work out because for some reason I think they had a bug in terms of what credits were used for the demo system and whatnot. But it just resonates with the idea that I just said, that you kind of connect a quantum device to a quantum system, you let it do its thing, and then that kind of maybe simulates or approximates consciousness or intelligence. I don't know, because it to some extent it feels a bit like what's kind of happening with nature, right? Like it's a bunch of quantum systems that, because they stay, they keep being entangled, and there's like a sort of a cascading entanglement with the environment. That's kind of what then turns things into classical. But yeah, I don't know. I haven't used the D-Wave system myself yet. A lot of people don't seem to think that's something worth trying, but I don't know. There's a bunch of people that do. There's recently some, I think it was Chicago Quantum. It's a I don't know if it's a company. They recently published some portfolio optimization stuff based on D-Wave, but I really didn't take a look at it. It seemed to actually have some interesting results apparently, but I don't know. I didn't go through this. And I don't know, from the paper, like they talked about, like they do talk a little bit about HHL, and sort of they give a really brief overview on these, but I don't know. The most interesting from my side was this mention of the quantum simulation, like a quantum simulator being a quantum computer that you connect it to a quantum system, and then you learn something from that system. That seemed to be interesting. And then there's like the whole control side of things, whereas machine learning actually being used for error correction and control of quantum devices, right? Like that's what the Q control guys are doing. I don't know if you've played with their products. They have like I think one is called like Black Opal, I think, and you get a free
Black
demo,
Opal,
and
yeah.
they have some cool interface in there to play with stuff. And basically what they do is they kind of, I think that's their area of expertise, right? So they devise machine learning strategies to kind of help you control and optimize the control of your systems.
I had a small question. So,
Hmm.
what do you think? What it could be you, Daniel or Wakiti. That what do you think that the type of qubit we are dealing, like quantum annealing, it is a topological or superconducting. What do you think is the best technology for quantum machine learning right now? Of course, because we don't know what will come in the future. According to me, it's superconducting, but quantum annealing is restricted to optimization problems. So you are not actually fully utilizing the you can say the strength of quantum computing. So, what are your takes on this? What do you think is the best technology which goes with quantum machine learning and give us the most benefit? You can say.
I mean, maybe I'll answer. I mean, to be honest, I don't know, and I feel like I shouldn't care, or at some point you shouldn't care. But maybe it's maybe less about the qubits, but it's about whether it's a device specific, a specific design, right? Like in the paper, they talk about like the possibility to design a system that's specifically designed to work with like QAOA, for example, or to implement QAOA efficiently. I guess that's maybe what you're saying. I don't know because, for example, all the light powered quantum computing, like the stuff with Xanadu, the photonic quantum computer, that basically allows you to do CB quantum computing, like the continuous variable that we talked last time about. This seems to be promising as well because it's a continuous variable model, so it feels maybe a bit more powerful than a discrete model, but I mean, it's just a wild guess. Um, I don't know. I don't think it's a matter of like maybe now it is right. Like, but once you get error correction and all this kind of stuff, like maybe it shouldn't matter. I don't know.
Yeah, actually, yeah, it is right now because as we have been talking, that we are at a stage in quantum machine learning that we are not actually utilizing quantum mechanics to a full advantage. So right now, it is a valid question, I would say. But in the future, when we have correct, you can say stronger error correction and error mitigation codes, then it won't make much of a difference because any algorithm could run on any technology. So yeah, I agree with you. But yeah, this question was more relevant in the current perspective rather than the future because we don't know about the future. And yeah, I agree. After a previous talk on Discord, I digged into continuous variable, and I have to believe that continuous variable can give us a better performance in some algorithms, especially when dealing with multiple value. You can say like you can say VQLS and HHL. So yeah, I agree with you on that.
Okay. I mean, Voiko, what do you think?
I don't know very well. Uh, I don't have a point of view for this. I don't care for. I'm more concentrate about the algorithm, not hardware.
Yeah. Okay. I think here we're pretty. I think we're pretty similar in terms of the interests.
Uh,
It's like more what you can
because
do conceptually. Yeah.
because soft is good for eternity, but hardware can change from time to time,
Yeah.
especially especially in quantum computing where we have so much option.
Yeah, exactly. I mean, and actually, there's another interesting area that the paper talks about. That is the usage of a quantum computer, right, to kind of help design the next generation of quantum computers. So kind of, and I found it really interesting because this is really similar to one of the papers that I was recently reviewing on the channel. That's from the group from Alan. I forgot his surname. I'm so bad at names, but basically they have a paper that's called I think it's quantum assisted design or something like this. So the idea is that now we're getting at the point where there's going to be like this, it's going to be soon impossible to simulate a quantum computer of the current sizes we're getting at because simply the amount of qubits is going to be too big. And so how do you improve the way that you design a quantum computer, right? Because when you design a quantum computer, I guess you can't afford on, like, you come up with a design and then you let it produce and then you test it, right? If some of the designs, the way you've laid out the qubits and the stuff, the way that you've set up the system is not optimal, it's really expensive. So the idea is to use a NISQ machine to simulate the properties of a potential design, right? So in the paper they talk about simulating the static properties, like for example, what happens with the existing layout of qubits versus the dynamic, like how do they evolve in time and how much like resistant to noise are and stuff like that. So and I really didn't dig enough into the details, but the idea is you put a design, you simulate it, and then once you're sure that that design kind of can work well, then you send it to production, right? So that I thought that was an interesting idea, right? That you use a quantum computer to design the next generation of quantum chips, so to say. Because I'm scrolling through the paper.
That will be a dream job for me.
Sorry?
It seems like perfect job for every quantum computing enthusiast. Designing quantum computer with quantum computer.
Yeah, exactly. I mean, you see, you come up with a design and then you simulate it and then kind of get a feeling of whether this is going to work or not, and then you send it to production. It kind of makes sense. I mean, to some extent, it's what's happening with classical chips as well, right? Like we currently use we use computers to design the next generation of a CPU, right? But I'm just browsing quickly through the paper, and I'm not so sure there was anything else that really caught my attention. I don't know. What about you guys? Any other topic that, like, because I didn't, there's this whole thing with quantum Boltzmann machines and a bit of the background, and I don't want to, I don't want to take away importance of those topics. It's just I didn't feel like, I don't know, I was not really tuned in for such a paper, kind of like I felt a bit more, I would have enjoyed something a bit more concrete, but I don't know about you.
They say that we can apply PCA and HashL and another algorithm in biology, but these attract me. But they don't say exact in which way, and don't give reference.
There's no. I was going to ask. There's no references in the paper about this.
Are references, but not for biology in special or medicine, or they escape from my eye. I don't.
Okay. Are you interested in biology and stuff like that?
Yes, I wish to apply it in molecular modeling.
That sounds cool. I mean, we could definitely, do a paper in the future that, was somehow
Yes,
related to this.
one qubit have some free paper about this.
Say it again. Sorry. Hi. I think either you're muted or I'm not. I didn't hear that last question well. I think I stopped hearing. I think you guys are both muted right now.
Yeah, I was muted right now. Yeah, no, I'm not.
Oh, now
I think what he said. I think what he said was there is some paper. He was mentioning I think the author, and he said that there's a paper about it, and it's a good paper.
Okay, then we can put it on we can suggest it on the channel. CJ is asking something on the live chat, saying, would machine learning be used for things like optimization for various restrictions like quantum errors for designing new quantum computers, or would it work in some other way? I mean, I think because that came in with a bit of delay, so I don't know if I answered the question already, but as far as I remember from the paper that I read, it was two things that they were simulating. It was not about necessarily about the quantum errors, but it was about, things like coherence time and stuff like that, I think. So basically, I think they were trying to simulate two things, as I said, the static properties of, for example, like a qubit, right? And then they were also talking about, like, not just the qubit level, but like if you put like 2 or 3 qubits connected into a subcomponent, then oh, you cannot hear you guys cannot hear me in YouTube right now?
I think he's saying that he cannot hear you here on
Put like two
Discord,
or
but
three qubits connected into a subcomponent. Okay, because I just now turned on the live stream and just heard my last sentence, so I'm definitely hearable.
yeah.
So what I was saying is that they connect a qubit, for example, they put a qubit, like they simulate a qubit, but they also simulate not only that, but they simulate also, for example, a bunch of qubits, like a sort of, if you arrange qubits into a component, and then that's your component that has, like, I don't know, say 5 qubits interconnected, and then you have multiple of those. You can also simulate how those like single components behave. And I don't remember exactly what was being simulated, but it was two things. Like, they called it the static properties and the dynamic properties. I think probably dynamic properties would be, how well, how well the thing is resistant to noise, or how is, the decoherence times and all this kind of stuff. I'm not really too much into the hardware stuff, so I'm probably saying BS a bit there, but yeah. Yeah, I see Voiku now is in the chat saying, "Hi, I'm here." Hey, yeah, cool. I don't know. I think that's basically really it from my side, at least. There's QRAM was good. I'm just trying to recap. So QRAM was interesting. The simulation was interesting for me. The connecting to other quantum systems. And as I said, I definitely, if we want to do more about QML, we should definitely do something with variational stuff, because there is a lot being done there in the area currently. I don't know, Mr. Swaggy, do you have any other sort of, I don't know, feedback or feelings about the paper that you want to talk about?
Not actually. So as I said, that the paper was a good introduction to anyone who is not into machine learning but still want to learn about quantum machine learning. It was able to connect the dots, and which connect, or you can say, currently connect quantum mechanics and machine learning. But I feel like, yes, the paper restricts itself to basically optimization problems and linear algebra problem. I don't know. I'm not much sure about machine learning because I'm not into that. So I'm not sure about that. But I think there could be more, and I think there must have been more research in this field. I'm not up to date on quantum machine learning research. So yeah, I think the paper was good, and it was a good introduction to anyone who is thinking of I think researching in the field of quantum machine learning. That's what I feel.
Okay, cool. I mean, if we should definitely dig into this more. So I'm happy that we're doing this on a weekly basis. I really think we should try to push. I mean, I'm gonna do it anyway, even if nobody comes to discuss. I'm liking this. I'm gonna keep reading a paper a week, and then at least give my thoughts. But I think if you guys can join for a discussion, it's always nice. I mean, I don't know. How's your brain right now after the whole Kiskit school?
It's fine. It's fine. Actually, the lecture was fun. We already know that James Houghton is a fun guy, and you can say a guy who actually explains tough things in a way that it seems fun.
Yeah.
So
He's the creator of the Hello Quantum game.
yeah.
And I kind of interacted with him a couple times. I'm hoping to get him on the Turn the Qubits Off show soon. He said he really would like to, and I think that can be fun as well. And now you're going to do the labs already? You're going to jump into this right away?
Yeah. I tried to solve the lab the day before, it actually piles up if I don't do it the day it is assigned. And it's not actually so big. It usually takes me 45 minutes maximum to get through with the lab. So makes sense that I complete it on the same day. So yeah, I do it on the same day.
Okay, cool. Yeah, I mean, I'm curious to know more about, like, get your overall feedback at the end of the whole thing. Yeah, I don't know. Is there anyone who's joining in the live, who's watching in the live, that has any questions that they want us to talk about anything? Like, otherwise, as I said, I shared like an invite in the channel, in the chat. If you guys want to join the Discord server, you're more than welcome to do so. I think it's a fun place, and we'll be up next week talking about hopefully the Kiskit summer camp feedback. If you guys, is it when is it finishing actually?
It's actually finishing on Friday. On 31st, there's
Oh,
a yeah, it's finishing on Friday. So I think maybe we can do an episode on Saturday, special episode sort of thing. If
yeah, we could do it on Saturday. So it's finishing on Friday, and you have like the it's the same thing. So on Friday you have lecture and lab, like a final lab.
no. The Friday it's not a lecture actually. The Friday it's a panel discussion. Actually, I think it matter actually. Aditya posted on the chat as well. So various dignitaries are invited, and they are going to talk about the future of quantum computing and the career aspects and prospects of quantum computing. So it's a panel discussion sort of thing. So we are not sure how long it will be. Usually lectures are 3 hours, but I'm not sure how long the panel discussion will go. So I would suggest that we do this on Saturday. I would
Yeah.
suggest, yeah.
Let's do this on Saturday. I think that's gonna be awesome. I really let's try to let's try to frame the same, like aim for the same time, like maybe 5 p.m. So it's easier for you because it's probably quite late now on your side of the world. But I'm really looking forward to these, and I hope we get all the other guys on board as well, like Amir and Giri, etc. I think, and CJ. I hope CJ can make it as well. I think that would be. I definitely would love to get your feedback on these. Cool. Yeah, I guess I don't know. I guess we're done. I'm really hoping. Okay, next week I'm gonna have definitely fun listening to all these and being part of the discussion. And then the other week we should really do something more concrete. I'd like us to get on a paper that actually has some practical stuff, and then maybe we can even get our hands dirty with it, and then kind of discuss the outcomes. That would be cool as well and entertaining for people. Oh, I see. Amir's just joined. Oh, maybe we'll get. Hi, Amir. He's muted though. Let's see, because I mean, you can definitely we can. I'm in for a longer chat if Amir's brain is still alive and he can give us his perspective and or his feedback from the paper.
Yeah, I'm also in because the lab has not actually been submitted yet. So I'll be awake till now. So it makes sense that I wait and listen to Amir because he is quite experienced in this quantum machine learning field and has much more insight than me actually. So I
Yeah,
would
yeah,
love to hear him.
definitely. So how did you find the paper, Amir? Oh, he's typing. I don't know if he's. Oh, problems with the microphone. No problem. No problem. No rush. No rush. Yeah, I mean he does. He's done some. He's done quite some digging into the field, I think, because he works with games and stuff, and I think there's definitely some stuff in there that is relevant for his day to day as well.
Yeah. He was the one who suggested the paper. So
Oh yeah, actually,
yeah,
you're
yeah.
right.
So it would be actually fair to hear about the paper from him. It makes sense. So we'll just wait for him. Still time. There's still time, right? Yeah, there's still
Yeah,
time. So
yeah,
we can
chill,
wait.
man, chill, man. I mean, I'm not in a rush or anything. I mean,
Yep. Yep.
probably I can stretch like 20, 30 minutes more. So okay, the microphone on the laptop of his laptop is broken, so he's trying to download the app. It's all fine. It's all fine, man. It's all fine. We'll be back soon. I think I'm gonna grab a coffee. Actually, I'll be gone for like 2 minutes. Yeah, while Amir is actually doing that.
Sure.
So stay
Sure.
tuned.
Sure. Sure.
Okay, can you hear me?
Yes, I mean, you are audible.
Yeah, let me see if I can. Okay, there, I'm on speaker now. Yeah, I'm going to share my notes. So,
Hi
I
guys.
took, hey,
So what's up,
yeah,
Amir?
so not much. I'm actually, I'm remote right now, so I'm using my hotspot on my phone, and
Yes,
I,
yeah,
I ran out the
Danny.
door, and I realized I didn't have, I realized that I didn't have my, my microphone with me. I usually have it at my desk because my laptop mic is broken. So yeah, so do we want to hop into the paper, or did you guys already like chat about
Yeah,
other things?
we did already. We talked like already quite extensively about the paper. So I mean, maybe you can give us your thoughts on these because you suggested the paper, and then we can kind of
Yes, can someone
jump
mute
in.
mute the YouTube because it's echoing. So someone please mute the YouTube.
Yeah, that's gonna be me. I'll mute when I'm not talking. Sorry about that. It's because it's on my phone.
Yeah, no problem. I mean, it was not echoing for me, so I don't know. Yeah, maybe you can give us your thoughts on the paper, and then we can jump in and make comments based on what we discussed. Because we discussed a little bit of everything, specifically the stuff that I mean we kind of found the most interesting, which is kind of not the linear algebra stuff. Maybe to summarize it, I think the three of us were more like the linear algebra stuff was less relevant, or it felt less important, or less interesting, and the rest was kind of more interesting. But maybe just go ahead and give us your thoughts.
Sure. By the way, while I didn't have my mic set up, I heard you guys affording me too much uh, uh, credit for this field. I'm fairly new at it, so the reason why I picked this paper was because I thought that it was a good overview instead of like jumping into one of the specific areas. You know, I wanted it to be a broad sweep of things as I dig into more deeper papers. So I I was I would say I was like 60% pleased by the paper in that, yeah, it called out some pretty significant areas where things like you know, we all heard about the quantum PCA many times throughout the paper. So yeah, overall, I mean, I was happy to have read it. It was just that, um, yeah, somehow I was wanting more, and I can't quite put all that into words. What were it, to not have you rehash everything? Um, I would still like to know what your take on the paper was.
So from my side, like kind of so the paper again, like I think I usually enjoy reading stuff that is a bit more concrete rather than like reviews of a field, especially because if we do the week thing, like it was difficult for me to say, oh, I'm gonna pick up some of the references and dig into these. But it definitely, at least because I saw QRAM again, I digged into these, and I can, like last time we were talking about what it really is, and you mentioned about accessing info, like accessing like the data in superposition, and it does seem to be like this. At least what I quickly read about it. But for me, I think the most interesting stuff was along the lines of like the part that talks about a quantum simulator, like as a synonym of an actual quantum computer, right? Like it's a system that simulates a quantum system being used to kind of figure out the quantum properties of a real quantum system. Like I don't know exactly. They mentioned this really briefly towards the end, but they talk about like somehow connecting a quantum computer to an unknown quantum system, and then tuning the quantum computer in a way that it allows us to understand the properties of this quantum system we're connecting to it. I'm assuming this connection maybe could be some sort of entanglement, or I really don't know. But this seemed to be something interesting to dive into, and I'll probably do so. That was kind of because the rest, like, of course, the paper didn't talk much about variational stuff because I think that's really before the time where the whole variational idea exploded. They do mention something about QAOA, but really briefly. And we kind of briefly discussed with the other guys here that basically we feel like that maybe that there's something more than just the typical or the current approach of kind of improving existing machine learning methods with quantum computers, but rather finding a uniquely quantum approach to machine learning somehow. But that's it. From me, it was really that simulation part of try to understand quantum systems or the properties of quantum systems without we like that we don't know, right? That we wouldn't be able to probe with a classical computer.
Yeah, and that's funny because that was all of I think one paragraph near the end, or maybe a few paragraphs. So the rest of the paper wasn't really that.
Yeah, I mean, for me, it's like I'm less. I don't know. For some reason, I'm less interested in the actual speed ups. I know that it's not a common opinion, like because I think mostly everyone in the field is discussing about like speed ups and how to make sure that we really understand there's a speed up. But I feel like there's not too much focus on uniquely quantum stuff. Maybe there's no, like maybe there's no, but like I feel that's kind of I mean that's where my interests float more, right? Like they float towards more this part of the field, and so kind of I think the bulk of the paper, at least the first half, and even a bit more than this, is really focused on how the quantum computer can speed up some of the linear algebra just naturally, right? Like with PCA stuff, like they say, yeah, well, the density matrix is the actual covariance matrix. And I mean, I like the way that they talked about the different problems, the input problem, the output problem, and all this kind of stuff. But oh yeah, Abby says he's got to go. Okay, bye. So yeah, I mean, I'm less interested in that part and more on sort of a more uniqueness of the quantum thing. But maybe it's just my ignorance, that like kind of keeps me interested in this. Like with maybe to give you like some more insights into this on what I'm thinking, because we discussed about this earlier as well. So the notion of like the current variational approach to quantum machine learning is you have the ansatz, right? And then you kind of design an ansatz and you kind of try to optimize or minimize or maximize like a cost function. And you do utilize things like entanglement in these setups, right? Like your ansatz kind of has like entanglement between different qubits and whatnot. But I feel like that this might not really use the full power of entanglement to some extent. And I did make a reference to the many worlds interpretation of quantum mechanics, which again, and I might be completely wrong, but this idea of we're constantly being entangled with the environment, right? And then it all splits and forms as different branches and whatnot. And I thought that maybe a new approach to or a bit of a different approach to quantum machine learning would be more towards connecting a quantum computer to an actual quantum system somehow, right? And then let it do its thing, or try to, I don't know, maybe even kind of connect multiple quantum computers and see what kind of interactions it can have between quantum systems. I really don't know. But I feel like the just using the ansatz approach, it doesn't seem to me like, maybe if we are able to scale this like 100 times, it will lead to something interesting. But maybe that's not what's going to lead us to AGI. Maybe that's kind of what I feel. I don't know.
I think that is quite a good assessment. Yeah, I hadn't thought about the. So you're proposing that you would hook up a quantum computer to another quantum simulator, so that you could deal with quantum data directly. Is that what you're saying?
Yeah,
Like two separate systems?
exactly, kind of. Because I mean, I really don't know what these kind of really means. As in, like the paper, it's as you said, it's really a paragraph at the end where they say you can explore, or you can probe the unknown properties of a quantum system by hooking it up to a quantum simulator, and the quantum simulator being a quantum computer. That's at least how I understood it. And I kind of it clicked a bit. It clicked to me that like maybe that's a way to approach machine learning to some extent as well, right? Like and I don't want to get too fluffy. I hate when like, I mean, it's not that I hate it, but like I know that if I start talking about consciousness and whatnot, like people are gonna think, oh, these guys smoking something. Um, but like if you think about our own world and universe, at least in terms of the current physics understanding of it, where you have, at least if you think about quantum field theory and whatnot, you've got all these quantum systems, and it's the entanglement with the environment that then leads to the classical world, right? Or at least that's what I understand. I might be totally wrong. And so maybe simulating these is what takes us one big step forward, rather than just sticking with the current let's approximate stuff, right? Like let's approximate, because we know we can approximate any function, using the current deep learning type of machine learning stuff, and let's make a quantum analog of these, and we just have the space that we explore bigger because we have entanglement and other stuff, and other things. So instead of doing it this way, it's saying, no, maybe it's really about interactions. Like maybe really, the part that we're missing to move the field forward is this kind of interactions between different quantum systems. That's kind of it's really probably a bit crazy. And chances are that this is just a stupid thought, but I don't know. I found it interesting from the paper perspective.
Yeah, what I like about that is it actually, I don't think it's a crazy thought. I think it kind of mirrors what is happening in the classical machine learning world, which is there's an area of machine learning called auto ML, and that's recently. I mean, it's been around for a little while, but recently it's gotten a resurgence because there's this essentially like they've given a machine learning algorithm basic mathematical skills, like a high school level of math, and then giving it three simple, like a setup for setting up initial state, a learning section, and a prediction section, and then using some part of genetic uh, algorithms. It then allowed this machine learning algorithm to basically go off and discover how to build itself. I mean,
Like sort of
build.
learning how to learn, right? Like kind of.
Yes. And what's cool is what was found out of that is that it basically discovered gradient descent and back propagation for very simple of like it's a very simple network. It's only got one hidden layer, I believe. But yeah, it's called Auto ML0. And so what's inspiring to take from that and what you're saying is, well, like what if we did that at a quantum level? But with like hooking a quantum system, like basically set up some basic parameters but not put too much bias in as humans, and just let quantum systems, it's kind of funny, let quantum systems discover other quantum systems. But it'd be interesting to find out like what might be discovered from that.
Yeah, it's I don't know. I think that can be an interesting. I really don't know. I wouldn't even know where to start. Like I think I would have to put a lot of thought into this, but it would be interesting to see some work in this direction. It's just like I don't know. It makes me feel right like this kind of interaction, sort of unsupervised interactions, right? Maybe that's a way to phrase it. Where is it this auto ML thing? Also, the idea of like you're kind of playing against yourself kind of thing, where the machine, like the algorithm, is actually trying to, is learning by playing against itself as well, or is it something else, Days?
That's more of the GANs, like the adversarial
Okay.
networks. I don't know if that played a part in this. Um, I don't think it had like that behavior of discriminating like between outputs of like, or trying to, yeah, like trying to uh, spoof itself, but it did have like an approach of pruning out less like worthy generations of itself. So it didn't like immediately what didn't use a greedy approach of basically throwing out previous iterations that were less like didn't minimize the cost as much.
Yeah. Okay. I
Or
see.
like or were suboptimal. It like kind of let them hang around a bit and would maybe do some more mutations on them and then finally give up
Okay.
on old approaches. Yeah.
Okay, I see. Because
Uh,
it really seems like it's maybe a naive way to think about it, but it's kind of, if you think about what produces the reality that we perceive, this is really the entanglement that happens at the quantum level that kind of ends up building and creating the world that we perceive classically. And not only these, but like there's another component to it, which is that we're always on, right? Like it's like I don't know. It's not a quantum system that you would find in nature. It's not something that you can turn off and on, right? Like, it's just kind of always there, right? And so this is something else that we can currently, like, you can't simulate that with you know a, with a neural network or like with whatever it feels it's more like a one pass kind of thing. And yeah, you can somehow store, like, you can persist your learning, right? Like that's like I guess what a machine learning system does is that it just stores the model, so that kind of somehow it means you're storing your learning, right? But I don't know, it's not what happens in nature, right? Because you have, and that's the idea of a quantum system, that you have so much information in there that you can't classically reproduce, that this information, because it's always there and it's continuously evolving, is what kind of, I don't know, maybe this is what makes you be intelligent to some extent. But again, this is probably a really big stretch between these and consciousness and intelligence, but who knows.
Well, I'll say not. I don't have much more to add about the paper itself, but what you're bringing up is pretty cool, because where it makes me want to go with it. Well, actually, I'm going to connect it to one part of the paper. So one part of the paper said, I think it was at the beginning, it said that the approach is like that perhaps the benefit here of quantum machine learning is to produce statistical patterns that, and this is where I think we've talked before about like higher dimensional spaces, like produce these statistical patterns that would be computationally difficult on a classical computer to do that. And so what you're describing, where you're talking about like the ansatz, is like, I'm almost wondering if or sorry, you were talking about like how you could store like intermediate results. I'm wondering if we could ever develop a way to like essentially learn initial parameters with these ansatz, and however we parameterize in that space, but to know that like the complexity grows much more once we move into like after our initial state is set up, and then we move into a larger Hilbert space with the operations that happen. And maybe a lot of learning goes on there, and ultimately at the end, if we could spit out new parameters, we'll never know like the complexity of the calculations that are happening in that higher dimensional space, but at least maybe we have the just the keys to setting off that same process again when we want to move further along. I mean, I am just describing the variational property of like but yeah, I wonder if like our parameters into that would
Like,
ever work.
I mean, are you like, is this idea along the lines of like what, for example, Wolfram is like, in the physics project, I don't know if you're familiar with his idea of how to build a theory of everything, where he assumes that basically the everything that it's in the universe can be generated just with a really simple system, right? Like a set of rules, like an initial state and a set of rules that transform the state. And if you let that system evolve, it will basically generate the universe, right? But he says these types of systems are sort of they are not like they are computationally irreducible. I think that's a term he's using, which basically means you can't really predict. You can't speed up the process. Like you can't just predict. Okay, if I have this system and this set of rules, and I'm going to simulate the next 1,000 steps. Like you can't do that because they are not the way this evolves. It's not deterministic. Is it what you're saying that maybe like if you maybe you would be able to define an ansatz and a set of parameters that if you could store this because that's definitely something storable, you could then reproduce a certain up to a certain degree a complex evolution or quantum process. I don't know. Is this what you're saying, like that in terms of storing the stuff?
Kind of. I was just looking at an analog. I'm not looking at and I am a little familiar with what you're talking about with Wolfram. And it's funny because it borders on like the sci-fi from Devs, or Deus, if you've seen the show.
I haven't,
Yeah.
but I definitely have it on the list.
Okay, so I won't spoil that part then. But what I will say is like with Wolfram and like I don't know enough about that, and I'm not even necessarily saying like predictions in terms of like in the time dimension. I'm just meaning like can we know like even with all the talk recently with the like in our summer school like with the Qiskit, like we're talking about QFTs and like what's happening in that larger Hilbert space that we eventually like have to like squeeze out of the quantum computer by sampling. And all I guess what I'm getting to is I'm fine with leaving the quantum like intelligence we have in that quantum like that larger Hilbert space if we can have the keys for continuing that like from a quantum machine learning standpoint, if we can have like the if we can somehow figure out how to get out the keys that can produce that same state if we are doing some additional computation.
Yeah, I see
So
where you're going.
yeah, in the terms of learning, like obviously we know what our circuits do in some way. We wrote them. Well, unless we get to a point where we're not writing them anymore. But and I guess what I'm saying is it would just be nice to be able to suspend because we have such short lifetimes right now with our T1 and T2. Could we like figure out an approach to quantum machine learning where we can essentially suspend the state and get out
and
the
then
next set of ansatz.
restart, and then kind of restart, and yeah. Of course, that would be that kind of would be probably a huge leap forward because then that's kind of you're basically able to reproduce the state you kind of left the state you were at when you left or when you kind of stopped, and then that would open the door to doing this other type of machine learning with quantum computers, I guess. And eventually, if quantum computers will get so good that you can, and I'm again risking to sound too crazy, right? But like maybe a quantum machine or a quantum simulator or a quantum computer is the actual machine that is able to simulate a universe to some extent, right? In terms of if you put in enough qubits and you just let it on, that's kind of what happens. I don't know. It's maybe a bit stretched, but yeah, I like the way I like that line of thought. Definitely.
And the funny thing is, I kind of think I'm not really saying anything novel at all in that. I think that is, in some way, like maybe at a from a different perspective, what variational algorithms are doing. But yeah, like it's less about a descent and more about being able to like suspend state. Like I guess one other way I've thought about it is separate from just having the parameters for the ansatz at the end where you could then iterate on that. I would love to see how we can perform almost like tomography, like a state tomography in our algorithms. Because wait, like think about it this way. So let's say we have a grand algorithm where at the end we're getting some useful information out. Think about the moment before you get that information. The moment before you do whatever final gates you have a state, you have a quantum state that is in some special state that when you run it through those final gates, you're getting out, intelligence or whatever you've been seeking to know. So some part of me wonders, like, could we have, even with our short timelines, if we have a way to suspend state, can we essentially have like arbitrarily long depth circuits if we could somehow like snapshot or perform tomography on the state prior to, the collapse of the system? I
Yeah.
don't know if that was just gibberish.
Okay. And then basically with these, you would just kind of chunk your huge circuit, like you would just chunk it out and then run small chunks. Right? That's what you're saying, right?
You got it. And then you could build around, like, you would know a portion of your circuit's going to go towards like preserving that or suspending that state. So, but then you chunk it more. Like, so let's say half of, like, if our timelines are only so long, half of it is your original algorithm that's been like chopped off at some point. Half of it's going to this tomography that I'm hand waving about, that I don't fully know how you would do yet. And then you're then starting your next block of your circuit with a new circuit that essentially recreates that state that you got with tomography. And then you continue with a new set of your next chunk of gates, and then you could go arbitrarily long. Now, is that possible? I don't know. I don't know enough to know what I don't know.
Yeah, I guess. I mean, for me, it's kind of you would. What seems obvious is that you would have to have a way to compress that. You know what I mean? Like, because it's right. Like, you can't just store like 100-qubit superposition, right? Like, it's. I mean, it seems theoretically impossible because you would need 2 to the power of like 100 pieces of information, and that's just too big. But yeah, I get what you mean. If there would be a way to kind of compress that and then be able to store these and then kind of unpack it and get going with the next batch of gates or of the next part of your circuit, that would be a huge step forward, definitely. Cool.
Yeah, I like how you're saying it in
Yeah.
terms of compression. It's like compressing your original circuit with whatever starting state you have.
Yeah, exactly. But the problem is that wouldn't this mean that if you're able to do that, you can just basically simulate it? Like, if you're able to, or maybe not, because you can't unpack it into a simulator. Okay, you can. So you can't just take like a compressed quantum state, so to say, and just decompress it in a classical computer. You can't, because it's just too big. Yeah.
Yeah, and I think what I'm referring to is if there's a way to like, yeah, we're not going to spit out the actual, well, I guess when I'm saying tomography, I'm saying, yeah, I'm trying to get all the amplitudes. No, you're right, that doesn't scale. It would be more about, can we get a compressed representation of the circuit that's needed to reconstruct the state at the end of that, whatever, like, yeah, at the end of our existing circuit.
Yeah.
So yeah. Anyway,
I'm kind of I'm sorry because I'm really running out of time. But thanks for joining. I mean, I think it was nice to have a chat with you as well on these and kind of get your perspective. We were talking before you joined. We were saying that maybe next week we should move the weekly Discord to Saturday, if that works for you. I don't know. And try to get basically, instead of a paper, just talk about the Qiskit Summer School, like what your experiences are, where, and like how, what did you learn and all that stuff.
Yeah, I'm open to trying it out. Let's try it out.
Yeah, let's
it'd be
let's
fun.
see if we find like a time slot. Like, let's just sync via Discord and then because I think that could be super valuable for people who are not able to join, and they might want to be willing to listen in and kind of see what your experience was.
Yeah, it could maybe even be the same time as we would do on
Would
Friday,
it?
since
Okay. Would it be over already at that time, like at 5 p.m. or 7 p.m. CET? So sort of the time now. Like, sorry, I'm talking about my from my time zone perspective.
Well, if you mean, but if we're doing it on Saturday, then I don't think there's any programming for Qiskit on that day.
But you're done. Like, when is the last day of the school? Is next Friday, isn't it?
Yeah, next Friday. So if you're proposing we would meet on Saturday, then yeah, then we would all be done already. Or are you
Yeah,
trying
yeah,
to say?
that's what I want. I mean, I wanted to discuss, once you're done with the school, with the summer school, to get you guys, to get a discussion going on, like what was your feeling and your experience with the course.
Sure. Yeah. I mean, I'm. We'll just have to see what time works for everyone.
Okay.
I'm open to anything though. Yeah.
Okay, cool. We'll do that then.
Cool.
Perfect. Yeah, man. Thanks a lot for the. It was a good paper. I mean, as I said, like I would always prefer. I would have preferred something more concrete, but I like the way that it touched some of those topics, and at least even if it was just a small paragraph at the very end that talked about the connecting to quantum systems and stuff like that. I found it interesting. It kind of clicked. It helped me click. I think. In terms of all these ideas of doing a bit of a different machine learning with quantum stuff. Cool.
Yeah, I think I'm done with the broad strokes of these types of the broad stroke papers now, and I very much will enjoy like going deeper with you
Yes,
all and
something
with the
more
community.
exactly, even something more hands-on that we could kind of play with, even, and kind of share, whether it worked, whether it didn't work, and what have we tried, etc. That would be cool as well.
Awesome. Well, thanks for hosting this as always. See
Yeah, man,
you
it was a pleasure.
next week.
Yeah,
Yeah.
see you next week. Bye bye.
Bye.